Hi guys, it is time to learn about aqueous solutions. I can't reiterate to you how important this lesson is going to be, as aqueous solutions is something that we will deal with all the time. Most reactions happen in what's called an aqueous solution. The word aqueous is just a fancy way of saying you have taken a substance and dissolved it in water. Those substances and the water and the solution that forms, they have special names. So if you look up at the top of your paper, you'll see the three terms. We have the term solution, we have the term solute, and we have the term solvent. Now you should be familiar with these from last year, but just as a quick review, what you'll do is you'll have your water-based solution most of the time. As you can see, this unit is called aqueous solutions, so our solutions will be water-based for the most part. So that is our solvent. It is possible to have other solvents than water. We will see some as we move forward in the course, but during this unit, all the solvents will be water because, again, it's called an aqueous solutions unit, and aqueous means dissolved in water. Now, that substance that we said we called a substance is really technically called a solute. So the solute is the substance that's being dissolved. The solvent is the substance that's doing the dissolving. And once you mix them together, voila, you have a solution. Now, it's really important, especially this year, that we identify what's actually happening on a particle level. Not just understanding those three words, but what is actually occurring. You'll see some pictures on your paper where it says step 1, step 2, and step 3. I also have an animation that we'll watch here. And the animation goes kind of fast. I might replay it a couple of times as we're talking about this. But that big clump of green in the middle is supposed to be some sort of solid, okay, some solute. We're going to talk about covalent solutes and ionic solutes here in a second, but it's some sort of solute that we have there. The red with the grayish ball on it, that is a water molecule. And if you remember from last year, you can see that it does have sort of a bent shape to it. If you look at this one in particular, you can kind of make out that bent molecule shape. I'm trying to find another one here. This one you can kind of see the bent water shape. The two smaller spheres are hydrogen, the big red one is oxygen. So what it's showing you, let me hit play again. Oops, 1 second. I use my pen, now it's mad. Okay, so I hit play again. You see those water molecules coming in and pulling apart that solute. That's the process of dissolving. When you pour sugar, for example, into a glass of water, at first you can see all the sugar there, and then slowly you start to not be able to see the sugar. We know the sugar's still there, because if we taste the water, it still tastes like sugar. This is not a chemical change by any means. This is all physical. We're simply pulling those particles far enough away from each other where we can no longer see them with our eyes. You would have to be looking at a much, much smaller particle level. Now, it does let us click this close-up view so you can get a little bit better look at it. You see the water molecules come in and attack and pull off that chunk of the solute. This image right here is just kind of showing you the arrangement of those particles around the piece it pulled off. This specifically is an example of an ionic solute, but this is true even if it was covalent. The same process would happen. So let's hit play again just so that we can get one more peek at it. So again, watch those particles come in. They pull off that solute particle, and what's left over here on the right side is what we would designate as the solution. This idea is going to be important because the water helps facilitate the reaction to happening. It helps give it a way to actually occur. When it pulls those pieces away from each other, now they're more susceptible to a reaction, whereas the solid itself might not have reacted. This leads us into a discussion called electrolytes. Again, a very, very important topic that we are going to see a lot of when we're discussing in this unit. Electrolytes, as you can see on your paper, says it's a compound that dissociates or breaks into ions when dissolved in water. So first of all, underline that word dissociates and kind of circle the part right next to it that says breaks into ions. When I use the word dissociate, it does not mean the same thing as the word dissolve. Dissolve simply means to place a solute in solvent and then no longer be able to visually see it. That's dissolving. Dissociating means once it has dissolved, so it has to already be dissolved, once it has dissolved, Does it have the capability to break into ions? This is where the whole discussion of ionic versus covalent is going to come in. Ionic compounds are made of ions, so they would be able to be pulled into ions. Covalent substances, however, are not made of ions. Covalent substances are made of two nonmetals, no charges, as we reviewed while we were doing our naming and our formula writing, no charges, so therefore we can't pull it into ions. We can't pull it into charged particles because it's not charged particles. So we have to be able to designate some different types of electrolytes, and that's going to be the main focus for our lesson today. I do want you to see a quick little video. It's only a couple minutes long, and it will give you an idea of what uses we will have for this topic of electrolytes, plus give you ways that we could actually test solutions to determine if they are electrolytes or not. Unfortunately, we don't have the equipment to do what they do in this video, so that's why I thought it might be a good idea for you to take a look at it. Now, I will say this guy is much more attractive than I am.
The term electrolyte is a term used when talking about solutions with water as the solvent. We'll demonstrate the property of being an electrolyte with an electrical conductivity tester like this. Pure water does not conduct electricity.
What he's done here is he's stuck this probe in there, and the probe is an electric conductivity tester. So if there was some ability to conduct electricity from that solution, it would allow that light bulb to generate power and show light. He's doing it in water, so obviously not a conductor, not a good conductor of electricity.
We'll put the electrodes of the apparatus into the beaker of water. There's no light coming from the light bulb. If I dissolve a material in this water and the light lights very brightly, the dissolved material is called a strong electrolyte. As an example, here is a small amount of table salt. I'm going to add just a little bit to the water and stir it up.
Now we're going to discuss in just a minute how he knew that table salt would be a strong electrolyte. That's going to be part of our lesson, but he already knows it because he understands the chemistry that I'll be teaching in just a few minutes.
As it dissolves, the ions of sodium and chlorine, which are charged particles, go into the water, which will now allow the solution to conduct electricity. So the ionic substance, table salt or sodium chloride, is a strong electrolyte. The term non-electrolyte refers to a substance which dissolves in water but does not allow electrical conductivity. Here is some sugar, which I will dissolve in the water.
So far he showed us water, which does not conduct electricity. Now he's making actual solutions. So he said the sodium chloride solution was a strong electrolyte, and he's told you that this sugar solution is going to be a non-electrolyte. So kind of think about, before I hit play again, what's going to happen to that light bulb when he puts the electrodes up to it.
As the sugar dissolves, the light does not light up. So
did you get it right?
sugar is a non-electrolyte. Some acids and bases are also strong electrolytes. Here's an example of some hydrochloric acid. Only a little bit in the water.
That's my favorite part of the whole video.
And about 10 drops. Will allow the light to light up very brightly. So the acid is also a strong electrolyte, therefore it's called a strong acid. Acetic acid, on the other hand, dissolves but allows very little electricity to go through the water. See how the light bulb gives off much less light with a lot more acid. Thus we call acetic acid a weak electrolyte, and it is a weak acid.
Okay, so it gives you a view, a visual of what could happen as a result of each of these solutions. And again, he was talking about strong electrolytes, weak electrolytes, non-electrolytes. What we have to learn how to do today is classify those without a conductivity tester. If I gave you 10 solutions in a conductivity tester, you could walk around and stick your electrodes in each one and know immediately. But you're not going to have that on you every single day, so we have to have a way to look at the solute and be able to tell, once that solute is dissolved in water, is it going to be a good conductor, an okay conductor, or a non-conductor of that electricity. So let's go ahead and start with strong electrolytes. On your paper, you can see the same list. There are really three things that are going to be designated as strong electrolytes, three types of solutions. If you have a solution of water and you put any of these three into that water to make a solution, you will end up with a strong electrolyte. So number one says, or on your paper it says A, all soluble ionic compounds. If you put any type of salt, ionic salt, not just table salt, but any type of ionic compound into water and it dissolves. So as long as it is soluble, that word soluble, circle it, and right next to it write it dissolves. So as long as it dissolves, then it will be a strong electrolyte. It will conduct electricity well. The reason for that is that all of these substances will completely ionize when placed in water. So let's say I'm going to take a substance like, let's not use table salt since that's, just the most common ionic substance there is. Let's say we take KNO3, okay, potassium nitrate. I picked one that had a polyatomic ion, okay, because again, that's still considered an ionic compound. It's made up of two ions, a metal and a non-metal or non-metals. So when I put this in water, it is going to completely ionize. It's going to break up into potassium ions, and then it's going to break up into nitrate ions. Notice the nitrate stays together. It doesn't break up into potassium, nitrogen, and oxygen. It breaks up into the ions that compound is made from, which is potassium and nitrate. And every single one will do this. Strong electrolytes have lots of ionic charge associated with them because all of the KNO3s will break up into K plus and NO3 minus. Now, every time we talk about this, we don't want to have to draw a beaker for it. So instead of drawing a beaker, what we're going to do is actually write an equation for it. And the equation is very simple. It's not a chemical equation. It's just a representation of what's actually occurring. So we're going to say that KNO3 is going to break up into, so I'm going to use an arrow to indicate that it's changing. It's going to break up into K plus and NO3 minus. Those charges have to be there because dissociation of KNO3 does not mean it's making pure potassium. It's making potassium ion, and there's a huge difference between K and K plus. So this is how we'll actually represent it on quizzes and tests and conceptually as we go through the class. But the beaker, I think, helps give you a nice representation of what's actually occurring. So ionic compounds do this. Any ionic compound will do this. There are also two other things that will do this, and you should remember this from honors as well. Strong acids and strong bases are considered strong because they completely break up. If you remember, that's what your chemistry teacher taught you. Strong acids completely break up when they're placed in solutions. Weak ones don't completely break up. So any of your strong acids from your list that you have learned will do the following. Let's say we have HCl, very common acid. We put that acid in water. It is strong, so I know it will completely break up and hence be a strong electrolyte. So it's going to break up into H plus and Cl minus, the ions that it is made up of. Now, again, we don't want to draw this beaker every single time, so we're going to put our equation down here because that's more how we'll represent it. We say HCl is going to break up into the ions that it's made of, which are H plus and Cl minus. Let's do an example of a strong base too, so you have an example of one of each of these. We know our strong bases are the group 1A metal hydroxides and group 2A metal hydroxides from calcium down. So let's use calcium hydroxide as our example. So when we put calcium hydroxide in water, being that it is a strong base, that means it is a strong electrolyte, and that means it will completely break up. So it will break up into Ca plus 2 and hydroxide. But we need to be really careful with this one, because if you look at the original formula, we have 1 calcium and 2 hydroxides. So if I read this like this, it's not actually correct. There are 2 hydroxides that are given off by each molecule. So you'll actually end up with 1 Ca plus 2 and 2 OH minuses for every molecule that dissociates. And again, every molecule that you put in will dissociate. So our equation would look like this. We'll say CaOH2 breaks up into Ca plus 2, and then you just say 2 OH minuses. Or you could say Ca plus 2 plus OH minus plus OH minus, but I like to use the coefficients because it's just shorter and easier. This equation writing that's below the beakers here, super, super important. Okay, so strong electrolytes completely break up into their ions. That's why they conduct electricity so well. And the things that are considered strong electrolytes is any soluble ionic compound. So if your solute's ionic and it's soluble, we'll talk about how to decide if it's soluble later. For now, you can assume that it's just soluble. So any soluble ionic compound, any strong acid, and any strong base, all of them, when you put them in water, complete dissociation. If we move on to weak electrolytes, the word weak is indicating it will conduct electricity, just not quite as well as the strong electrolytes will. The weak ones are pretty easy. They're pretty straightforward. The only things that are weak electrolytes are weak acids and weak bases. That's it. And you already learned last year that that word weak with acid or base means it does not completely dissociate. It does not completely break into its ions, but it does partially break into its ions. So let's do an acid so you can see this. We'll use the acid HF. Hydrofluoric acid is not a strong acid. It's not one of your 7. So when we place it in water, it will partially break up. It'll produce some H pluses. It will produce some F minuses, but not all of the HFs will do that. So therefore, in your beaker, you also need to represent HFs that will remain. So we're going to have HF, we're going to have H plus, and we're going to have F minus. Second semester, we will spend a lot of time talking about how much we end up of each of those substances in that beaker. But for now, you just need to understand that it doesn't completely dissociate, which is going to give us a problem when we write our equation. Because if I was just to write HF breaks up into H plus and F minus, because this is an equation, it's telling the reader that this is the only thing that's present when you're all done with the reaction. But we know that's not true. This thing is weak. So instead of using a single-sided arrow, what we will be using is a double-sided arrow. If you remember from last year, double-sided arrows indicate something called equilibrium, and we'll get into equilibrium second semester extensively. But in order to represent in an equation this guy, what's actually happening, what we see on this beaker picture, we have to draw it this way. The double-sided arrow is pointing to both sides saying, hey, reader, look at me. Everything written in this equation is in this beaker. It is not a one-sided situation. We can do the same thing with a weak base. We learned that, which one do we want to use? Let's use CuOH2. Copper hydroxide, not one of your strong bases, so we are going to get some dissociation. We will get Cu plus 2s. We will get 2 OH minuses for each Cu plus 2, so I'm writing my ratio correctly there in my beaker, but I'm definitely going to have CuOH2s left. So that's what my beaker would look like. We don't want to draw a beaker every time, so we're going to put CuOH2. It's a weak electrolyte, so I need a double-sided arrow, okay? And then I'm going to put my Cu plus 2 and 2 OH minuses. And that would be the equation we'd want to use for that. So strong acids and weak acids, I'm sorry, let me say that again. Strong electrolytes and weak electrolytes we will represent with equations more often than beakers. The difference between their equation is a double-sided arrow. Very, very important concept and idea to understand. Now there is one more group called non-electrolytes. Non-electrolyte indicating that it does not conduct electricity. Covalent compounds fall into this category. And we already said the reason is because if it is covalent, it doesn't have ions. If it doesn't have ions, it cannot conduct electricity. So any covalent compound will not conduct electricity. And you can see on your paper there that designation for covalent compounds. Let's just use as an example C12H22O11. If I put sugar in water, it dissolves. We all agree. But it does not dissociate. So if I was to represent what that molecule looks like once it's in the water, it will look exactly the same. It's just broken up into enough small molecules that I can't see it anymore. But the molecule does not change. So you see no change here. Another one I could use C2H3O2. Put that in water. It will still be C2H3O2. No different at all. We really don't write equations for these because it wouldn't make any sense. If we wrote an equation, it would look like this. C12H22O11 yields C12H22O11. It didn't change. Sure, single-sided arrow, I can make it a double-sided arrow. It doesn't really make a difference. It all says the exact same thing because those molecules just got away from each other. They did not change the way that they were adhered to each other. So that is a covalent compound. It's going to fall into this category, again, you can see up here at the top, of a non-electrolyte. If you put those conductivity probes in here, nothing happens. Just like putting it in water, there's no conductivity, not enough to light that light bulb. Okay, so if we take a look, we've got some different compounds here. For these, let's start. The first thing you have to do, it's kind of like naming. The first thing you have to do is decide, is it ionic or covalent? So go down each one of these and determine if it's ionic or covalent. You can pause if you need to. Barium chloride is ionic. Got a metal and nonmetals. Calcium nitrate, ionic. Metal and nonmetals. C2H12O6, covalent, because it's all nonmetals. So now if I'm asked to describe what type of electrolyte this is, for BaCl2, since it's ionic, and for now we will assume it's soluble because we haven't learned any different. So since it's ionic, I know it's a strong electrolyte. Okay, why'd I write strong acid? I have no idea. Strong electrolyte. Since it's CaNO3 is ionic, again, ionic ones. For now, you're assuming them to be soluble. Strong electrolyte. If it's ionic, it is a strong electrolyte. How about C6H12O6? All nonmetals. We said it's covalent. If it is covalent, it is a non-electrolyte. Okay, so it's a matter of classifying, just like we did with naming and formulas, and knowing which fits into each classification. That's some more examples for us to look at here. So CCl3. CCl3, we have nonmetal and nonmetal. So let's, for these ones, instead of just writing whether or not they're strong electrolytes or weak, we'll decide that first, and then we're going to show the equations that go with each. So this is a covalent compound. Since it's covalent, this will be a non-electrolyte. Since it's a non-electrolyte, we can't write an equation. This is that instance it wouldn't really change. For HCl, we know that HCl starts with H, therefore it's an acid. So we have to think, is it a strong acid or a weak acid? We know it's a strong acid. If it's a strong acid, then we know it is a strong electrolyte, because all strong acids are strong electrolytes. Since it's a strong electrolyte, let's write its equation. So HCl is going to break up into its ions. Its ions are H plus and Cl minus. Next one, I've got a hydroxide. That's an indicator that it's a base, so we know it's a base. Look at the first part. Cu is not one of our strong bases, so this is a weak base. Any weak acid or weak base is considered a weak electrolyte. And weak electrolytes, we're going to write equations for, but we're going to use a double-sided arrow. The double-sided arrow, again, is going to indicate that both sides of the reaction are present. So that means in this beaker, there is CuOH2, there is Cu plus 2, and there are 2 OH minuses for each time this thing breaks up. For HCl, this was all that was in the beaker. H plus and Cl minus, single-sided arrow. All right, next one, NaOH, base. Na is one of your strong bases, so a strong base will be a strong electrolyte. Strong electrolytes completely dissociate. So we're going to write the dissociation as NaOH. It's going to break up into its ions, which are Na plus and OH minus. Do not break up the oxygen and hydrogen because you're supposed to break it into the ions it's made up of, sodium and hydroxide. Really what its name was indicating probably is a good way to think of it. All right, next one, HF, acid, but it's a weak acid. Weak acids will be weak electrolytes. Weak electrolytes do get equations, but they're special in that they will have a double-sided arrow. So we'll have H plus and F minus. So the classifications of these is very, very similar to the process you follow for naming. In naming, we have to look, is it acid or base? Is it covalent? Is it ionic? That's the exact same process you want to go through here. If it's an acid or a base, you then have to ask yourself, is it a strong acid or a strong base? Or is it a weak acid or a weak base? Because that will tell you strong or weak electrolyte. Those words match up on purpose. Then if it's not an acid or a base, then move on to just plain old ionics. Look to see if it's ionic. Does it have a metal? If it doesn't have a metal, then see if it's all nonmetals. And if it is, you've got a covalent compound, which is going to be a non-electrolyte. So it's a matter of learning those classifications. As long as you do that, you should be good. And again, this idea of ionization, this idea of breaking up into ions is extremely important when it comes to concepts that we are going to discuss. These things have to ionize first or not ionize, if it's, say, a covalent compound, for it then to react. And with those weak electrolytes, if they're only partially ionizing, that's going to affect how they react as well, because we only have certain ones that will be ions. So go ahead and go back and rewatch any part of this video you're not sure about, and we'll spend some more time in class discussing this on a sort of different level.